Okay, well, good morning. Today we're going to do a lecture on resonance theory. Resonance theory is a very important theory in organic chemistry that we'll use a lot here in 242. So that's why we're going to cover it at the beginning of this class, and then it will carry throughout the rest of the semester. Resonance theory is covered in the book in chapter 1, but even though they put it in chapter 1, it doesn't mean it's a very easy concept. And so we're going to cover it now after we've had a semester of 241 under our belts and see how we can use this in our favor. So when we study resonance theory, what we can do is look at a couple of molecules. For example, if we look at methanol, it has two lone pairs on the oxygen atom. And what we say about these lone pair is that they are localized. What does it mean if electrons are localized? That simply means that they are stationary to that particular atom. The lone pair are on oxygen, not on hydrogen, not on carbon, but on oxygen only. And so that's what we mean by localized electrons. Let's draw another molecule. If you look at this molecule below, here, again, we have two lone pair on oxygen, but we also have a positive charge on the adjacent carbon. And what we can do with this structure is write another structure that looks something like this. Where here, if you look, this lone pair on top of the oxygen is no longer there. They have moved to form a pi bond, and so give you a double bond at this spot. And notice too that the positive charge has moved from this carbon to the oxygen here. And so what we say is that these lone pair are not localized, but rather they can spread out from this oxygen all the way over to the carbon and forming this double bond. And when electrons can do that, we say that they are delocalized. So these electrons on the oxygen, one of the lone pair, are delocalized. They go from the oxygen and spread over to the carbon. We'll be looking at some rules later on to see how and why this can happen. But here we've understood two very important concepts: localized electrons and delocalized electrons. And what we say is that if a structure has delocalized electrons, that these two structures are what are called resonance structures. And the way we indicate resonance structures is by using this double-headed arrow. Okay? So delocalized electrons always invites the drawing of resonance structures. And that's what we want to learn. How can we predict if a particular molecule has resonance structures? Okay? And we will find out that molecules that have resonance structures and so have delocalized electrons, they have very special properties associated with them. And so we'll be investigating that as well. So let's go ahead and investigate resonance theory by looking at some rules of drawing resonance structures. Okay, the first rule of drawing resonance structures is when we have a lone pair next to a positive charge. If you recall, we saw that in our example we just looked at. Let's go ahead and draw that example again. Okay, so here we have lone pair next to a positive charge. And so the rule is that the electrons can dump toward the positive charge and so form a pi bond. So we can show that with an arrow. And so show our second resonance structure. And recall the formal charge moves over to oxygen here. Okay? So I can show this arrow dumping toward. It's almost like what we can call the mechanism of drawing a resonance structure. Okay? Because electrons migrate toward the positive charge, and so we get that. And so here, these two are our resonance structures, and because so, we can use this double-headed arrow. Okay? So that's what we're going to do. We're going to look at a bunch more of different rules, and I'll draw an example under each rule. And then we'll come back at the end and look at some more examples and try to figure out which rule we are to use and so forth. Okay? Let's look at our second rule. Our second rule, very critical rule, is when we have a pi bond or a double bond next to a positive charge. Let's take a look at an example of this. So here we have a molecule. Here's our pi bond, that's part of a double bond, and next door is a positive charge. Note the positive charge is on the adjacent carbon. It's not on this carbon, but it's on the carbon next to where the pi bond is. So what can we do here? Well, if you remember in 241, when you see a pi bond, that pi bond, in a sense, acts like a lone pair, or in a sense acts like a base. And so we can dump those toward the positive charge to make the double bond move here. So let's go ahead and draw that. So the double bond comes here, forms here, and note the trade-off is the positive charge now goes over to this carbon because this carbon is electron deficient. So this carbon was electron deficient, positive, and now this one is. So these are two resonance structures. And this kind of molecule has a very important name, where when we have a positive charge next to a pi bond, this is what's called an allylic carbocation. Okay? So an allylic carbocation is when we have a positive charge next to a double bond. Okay? There's other examples of allylic carbocations. For example, I could have one in the ring, okay, where I have the positive charge next to a double bond. And so this would be an allylic carbocation. As we go through these rules, and as we go through the rest of the semester, we will be spotting out allylic carbocations. They'll be jumping out very quickly because as soon as you see one, you'll be able to very quickly draw a resonance structure. Okay? So these are the first two rules, which are probably the easiest rules. Okay? Let's go on and look at our next rule. Our next rule is when we have a lone pair next to a pi bond. Okay? Let's take a look at an example of this. If you look here at this ether molecule, this vinyl ether, we have lone pair, and they are next door to this pi bond here. So this is the setup. So let's see how the rule works. The rule works where the lone pair moves toward the pi bond. And the pi electrons will dump onto its carbon on the end. Okay? So So electrons move toward the pi bond. So let's draw the result of this. So here's the result of our movement of electrons, where a double bond forms here, because these moved in, and this is moved to that outer carbon. So let's put that lone pair there. Note again, oxygen has 3 bonds to it, so that always gives it a positive charge. And this carbon has a lone pair, so it will have a negative charge. Okay? So note that the charges balance out. A negative and a positive cancels to neutral, and of course this molecule, this structure here, is neutral. Okay? So you always want to keep check of that your charges are the same on each side. Okay? So if this is neutral, this one had better be neutral. Okay? So this is probably the most difficult rule to keep in mind, and we'll do some practice of that later on as well. Let's look at another rule. This rule here is where we have allylic radicals. Okay? What's an example of an allylic radical? Okay? Remember that a radical is a single electron that has no charge, and it's allylic. Why? Because it's next door to a double bond once again. Okay? So the resonance structure for this is going to be basically the same as an allylic carbocation. In that the single electron jumps over here and the pi bond moves over here. It's almost like a trade. Okay? So this is an allylic carbocation, or an allylic radical, that sometimes we'll see this in action. Okay, so those are our main rules that we're going to use for drawing resonance structures. Okay, so let's go over some practice of these things and see how they're used in other molecules. And these are kinds of problems that you would see on an exam, where I give you a structure and ask you to draw resonance structures. Let's, for example, look at this molecule. This is taken right out of your homework problems. Okay? And if you want to keep your notes open and try to figure out which rule would you use. Okay? Obviously you won't be able to use these rules on the exam. You'll have to memorize them. But as we practice them more, you won't eventually have to say, oh, I used rule 1 or rule 2, but it'll be natural how to draw these things. So, what would I do here? Well, I got what? A lone pair next to a pi bond. So, the rule says that I can move a lone pair toward the pi bond. So if I do that, I get this structure where a pi bond is formed here, and these pi electrons came up here, okay? Okay, so if you're keeping track of things, that lone pair was pi electrons. So, are there going to be any charges? Yes. Okay. We do the formal charge of oxygen. We have 1, 2, 3, 4, 5, 6, and then 7. So this has 7 electrons around it. Oxygen is in group 6, so we have 1 extra. So it has a negative charge. And the nitrogen must have what? A positive charge, so that we have electron balance or charge balance. Okay? And if you work out nitrogen, remember nitrogen is in group 5, and it has 4 electrons around it. So if you subtract, that's another way to prove that the formal charge is 1. Okay? So you should remember this from general chemistry, 141. Let's take a look at another example. Let's look, for example, at this one. Where if you look, we have a positive charge here, and it's next door to what? A pi bond. So what kind of positive charge is this? Do you remember? Right, it was the allylic carbocation. So let's go ahead and draw some resonance structures. So remember, I move the pi electrons toward the positive charge. So when I do that, the double bond forms here. And remember, the positive charge trades down to here. And these other double bonds I just left alone. Okay, I didn't use those. But when I do that, what do I have now set up? Positive charge next to a double bond. So another allylic carbocation. So I can draw what? Another resonance structure. So I can move that there. And the positive charge moves over to this carbon. Again, I leave the other double bonds alone. I'm not using those. But what do we have once more? positive charge next to this double bond that we haven't used. So let's use that one. And when those come down, the positive charge trades to up here. And so we get our last resonance structure. So here's an example where I have more than one resonance structure. And you can indeed have that. You can have two, you could have three, you could have four, you can have a lot, as long as the molecule invites that. Note too that the positive charge was what? Heavily delocalized. See that? It was up here, and then it came in and spread all the way around the ring. Okay? So we have a lot of delocalization. And here we can make a comment. When a charge has lots of delocalization, then the charge becomes extra stable. So this positive charge has a lot of what we call resonance stability, because it has lots of delocalization. It's what? Spread out a lot throughout the molecule. Okay, so here we're getting these extra terms that you want to remember. Okay, delocalization means it's spread out. Okay, when we have this extra stability, that's called resonance stability. Okay, and it can happen both with a positive charge and also a negative charge. Okay, let's look at another example with a negative charge. Here we have a negative charge on oxygen. Okay? Remember, oxygen is neutral if it has two bonds. If I take away a bond, it becomes negative. If I had three bonds on oxygen, it would be positive. But here, oxygen is negative, and we got these three double bonds in here. So we can use what rule? Lone pair next to a pi bond. And remember, the lone pair moves toward the pi bond. And those pi electrons move to that end carbon. So if we draw the resonance structure, we get this here, where the lone pair has now formed what? A pi bond to give us a double bond here. And this now becomes a lone pair, which is on this carbon. But if you look, we can do that again, move these toward the pi bond, and so keep using our rule. So we move those over. And lastly, we can do that one more time. To give us our last resonance structure. Okay? Again, notice we keep charge, negative charge throughout the whole system. Okay? So this negative charge has high resonance stability, just like our positive charge in our previous example. Okay? So these are examples of all the different rules we can use. Let me give just one more example where now we can combine rules. Let's come back to a molecule that's similar to what we've seen, but now we have a positive next to lone pair, and we have pi bond next to lone pair. So what can we do? Well, we can use two different rules. Let's use one rule where we move the lone pair toward the positive. So if we do that, we form a double bond here, and now the positive has moved to oxygen. Again, note, oxygen has 3 bonds. Anytime oxygen has 3 bonds, it will always have a positive charge. But if I come back to this, I can use my other rule. So let me erase this arrow. And use the other rule where I move a lone pair toward the pi bond. And so we get a structure like this that looks very awkward. Okay? Hopefully that looks awkward to you. But it is a viable resonance structure. Okay? So the lone pair is formed here, double bond here. Oxygen with 3 bonds gives it a positive. This positive didn't move, so it stays there. And the lone pair on carbon gives it a negative charge. Does everything add up to a net positive charge? Yes. Negative and positive cancel, then we have a net positive here. So our charge balance stays the same. Okay? So these are different examples of how to do resonance structures. What I encourage you to do now is go into your homework and practice drawing these things. Practice till you get sick of them, because you're going to be using them in later chapters. So if you don't understand this now, you will be very lost later on. I promise you that. Okay? So make sure you get on this in your homework. Okay, so that was everything from chapter 1.9 in your textbook on resonance theory. And now what we're going to do is get into our next chapter. We're going to jump into chapter 15 and start talking about a class of molecules called dienes, okay? And see what kind of properties those have. Okay, so if you have your textbook, you can turn over to chapter 15. It's on page 667. And let's look at the topic of dienes. Okay? So you might remember what dienes are. Simply molecules with two carbon-carbon double bonds. Let's go ahead and draw some examples of dienes. Here are three examples of dienes that we want to give definition to. Okay? So note each of these has two double bonds in there. Okay? This one here, they're simply right next door to each other, so that dot represents a carbon atom. And we're going to give these things names. Okay? If you have two double bonds that are separated by two or more single bonds, we say that those double bonds are isolated. If the two double bonds are separated by just one single bond, we say that those double bonds are conjugated. Okay? So remember, conjugated, separated by one single bond. We'll see later that conjugated dienes have very important properties. So make sure you remember what conjugated means. And the last type of diene is what's called cumulated, where there is no separation, there is simply next door to each other. Okay? So make sure you know what isolated, conjugated, and cumulated double bonds are. It turns out that conjugated dienes stable type of dienes that you can have. Okay, they're more stable than isolated and accumulated. Okay, so when we're dealing with conjugated double bonds, they give the molecule extra stability that you want to remember. Okay. So one of the big things in this chapter that we're going to do is to look at the chemistry of dienes, okay? And that's what the next big section we're going to look at is how do these things react with some different molecules. So, reactions of dienes, this is what we're going to get into in our next lecture, now it's the end here. So, with that, we'll go ahead and close here.